All right, so you've got a system in mind that you want to study, and you've heard a lot about different methods that you can use to explore the local sequence landscape. But you find that your particular system has two properties. One, it's quite long, and two, it's in sequence space, it's very diverse. So what do you do? So as you heard yesterday, I developed this technique called DropSynth, which allows us to assemble very large libraries of very diverse sequences. And this particular approach excels if you have a limited subset of sequences that you want to explore. And so any kind of questions that you've built models, or you have very well-defined hypotheses where you want to explore very well-defined regions, this is something that you can look at. And so I'm going to talk about several different things today. First of all are several factors to consider. So is DropSynth even the right approach for you or for your particular problem? And I'm going to talk about that in terms of different types of libraries, length, scale, uniformity, cost, and yield should be in there as well. And then I'll give a very brief overview of the kind of typical timeline that you'll go through, experimental tips, and touch briefly on what's needed for computational design. And so actually, before I go there, I would just briefly want to make a comparison between Allago arrays and DropSynth. So, and if you think about what each one is actually good for. So as you already heard, Allagos are kind of limited to about 200 to 300 base pairs. DropSynth at the moment, and I'll get into this in a little bit more detail, excels basically between about 300 base pairs and about 1 KB, depending on what kind of yield you're willing to tolerate and some of the other factors. In terms of scales, you can order microarray chips at the level of hundreds of thousands. If you're willing to invest a lot in your DropSynth libraries, you can get tens of thousands. If you're really willing to push it, maybe 100,000. In terms of uniformity, the arrays, if you believe the vendors, are pretty decent. DropSynth is pretty poor, as you will see. So that's something you have to live with. And in terms of the cost, individual Allagos can range anywhere from several cents to several tens of cents each. And DropSynth is primarily, the cost of DropSynth is primarily a function of the cost of the underlying Allagos you actually use to do the assembly. And so to give you a very rough idea, estimate, it's just going to be the number of Allagos you use in each gene times the number of costs for each Allago, plus a small little factor of 10–20%. Okay, so there's two different types of libraries. We've heard a little bit about non-coding regions. Mostly the talks have focused on protein regions. In terms of DropSynth design, as you heard yesterday, we use several enzymes, BSPQ1 and BTS1, to do various processing at different steps within the library assembly. And so what that means is with protein regions, we can exploit the codon degeneracy to really very easily remove these types of sites, whereas that's a little bit harder with non-coding regions if there's certain things that you're not willing to mutate. And you can see the kind of typical frequencies given the fact that this is like a 6 base pair, and this is a 7 base pair site that you'll kind of encounter in random sequence. With protein sequences as well, you can take kind of advantage of synonymous mutations that are present in there and use that data as well. And you can go for either full-length proteins or split it into domains. And so I want to talk a little bit about what I think are bad applications and what are good applications. So doing a deep mutational scan with DropSynth is not the way to go. It's probably a waste of your time and money. That being said, there are potentially a lot of good applications that this opens up, such as if you have a limited set of higher order mutations that are relatively far apart and you can actually fit on an oligo, or you want to study epistasis on a relatively limited set. If you have a protein family that you want to synthesize in full length, and the lengths work into the lengths that we can synthesize. If you have a family of domains that are in such a way that you can fuse them using protein engineering to other required domains that you can maintain in a conserved fashion, this could potentially be a useful way. things such as ancestral sequence reconstruction or looking at the evolutionary trajectories between two different points in sequence space could also be several interesting things to look at. And of course, for non-coding applications, the obvious things are promoter libraries. If in the case of your promoters, you know, you want to look at lengths far above what you can put on an oligo, enhancer libraries, and so on and so forth. And so the length. So what can you achieve with current DropSynth technology? So here I've kind of broken down into what you'll find on any given DropSynth oligo. And you see that the regions highlighted in red are basically the regions that we use for processing. So you'll see typical things like, you know, forward and reverse amplification primer, two nicking restriction sites, which you use to expose the 12 base pair barcode, and a type 2S temperature sensitive cutter, which we use to release the so-called payload off of the bead during assembly. And so all of these sites added together basically add up to about 70 nucleotides of required non-coding sequence that you're gonna have to use on every single oligo you order. And so this kind of defines the scaling of what you can assemble given a certain oligo length. And so to give you an example, what we've done quite a bit in the past is around 4 oligos with 230 mers, giving us just over 500 base pairs that we can put on. I'm currently in testing out 4 oligos with 300 mers, giving us about 800 base pairs. And I think depending on those yields, it will be relatively trivial to scale up a little bit more if you're willing to take the hit on yield. That being said, one of the other interesting things about the 70 base pairs that you have to dedicate to this processing is that any errors in that 70 base pairs will be selected out in one of the steps in. So you can imagine that if there's primarily deletion errors in any one of the restriction sites or the barcode, there's going to be a very strong selection to remove those as well. So that does give you a little bit advantage in terms of selecting out some of your perfects. All right, so what we've done in the past is if you look at different length oligos and the number of oligos per assembly, we've done 4 or 5 oligos with 200 and 300 mers, giving us 400 or 530 base pairs of coding region that we can put on there. And these have been basically amenable. These are the boxes highlighted in red, or with the red border, are the lengths that are still amenable to like Illumina MyC characterization. Anything with lengths beyond this, you're gonna have to go to a long read approach such as PacBio. We've done gel verification for several longer lengths, and I'm currently working on doing some more detailed NGS characterization of 300 mers doing 800, and hopefully if the yield is good on that, we'll go to some higher lengths. So what I should say is I think in the very near future, depending on the yield of this, it should be possible to hit about 1 kb. That should be relatively straightforward with yields that we've seen can work in the past. So what about scale? As I mentioned yesterday, the initial version of this protocol we had built using 384 uniquely barcoded microbeads. We scaled that up recently in a preprint that's online to 1536. What we've seen in the past, and we've assembled now dozens of different libraries, is that we expect between 0 and 10% of the libraries to fail, primarily due to subpool assembly, subpool amplification issues. We have seen that. We're not quite sure what the source of that is. The typical coverage that you see, and I'll talk a little bit more, I think, about this, is about 70%, so ranges from 60 to 80%. And so what that means is you really have to build some redundancy into any controls or critical sequences that you add into your library, because some random sequences are gonna essentially fall out due to a variety of different reasons. And we've quite often in the past actually assembled all the protein libraries in 2 different codon versions and then basically subsequently mixed pooled them together in order to both achieve higher coverage and increase our overall representation. And so something that's realistic for a person to do is about 30 libraries in 2 weeks. It's a very busy 2 weeks, and that doesn't include NGS characterization, but that gives you kind of an idea of what the time scale involved in terms of at what particular scales. So uniformity is still a serious issue, and so this, we believe, has its roots in 2 different effects. One are synthesis effects in the underlying oligos. As I said before, most vendors will claim that you have very good uniformity in your oligo distribution. Of course, it depends what you synthesize, and there are definitely sequence effects with certain motifs causing lower representation. That being said, if we look at, the Gini coefficient is essentially a measure of inequality in a distribution, with perfect uniformity being represented by 0 and perfect inequality where 1 is all being represented by 1. So you can see we typically get Gini coefficients in the range of 0.7 to 0.9, which are not great. And so what this means is that you'll really have to think about the sequencing depth you require in order to basically start to pick up some of this tail end lowly represented genes that are in the library. And so what we've also seen is that when we've sequenced the oligos straight off the chip and then compared that to the assemblies, there is a very strong correlation between oligos that are very weakly represented at the chip level to the subsequent representation at the assembly level. And I should mention that one of the things which also contributes to this skew, which we're investigating, is of course the multiple rounds of PCR amplification that we go through, and we're exploring a number of different options to try to see how much of an effect that is on things. And so I mentioned yesterday that we have a yield currently about 25% or so. Here you can see yields for 2 libraries at the 1536 level and 1 library at 384 level, and you can see the typical distributions of how they range. With yields in this kind of region, I think you really have to take into account, considering also the skews in the distribution that I showed previously, what you're using in terms of your particular downstream assay and whether you can oversample in your functional assay enough that you can actually pick up everything that you want to pick up. So we've had people come to us and be interested in synthesis of library only to tell us that they were using colony picking robots downstream. So that's not gonna really cut it to these factors. I also wanna mention frame shift removal. We've looked at a bunch of different ways to do this in the past. There's a very well-known technique if you're synthesizing a protein library of just fusing it with some sort of resistance marker in frame to try to get rid of your frame shifts. Now, we've done that in the past, and there is some enrichment. I would suggest you look at that particular option if your particular protein has very few methionines downstream, because what we've seen is that the ribosome can actually restart translation back in the correct reading frame after the frame shift has occurred, and basically kind of killing your enrichment. So while you do get an enrichment, any kind of downstream ATGs can kind of can be a pretty large issue there. All right, so costs. What I'm showing here are basically the kind of costs exclusive of labor, and I think pipette tips is the only other thing that's not included on here at both the 384 level and the 1536 level. And what you're seeing here is that to build a batch of beads at the 384 level, you'll require about a $4,000 investment, and it works out to about 11 cents of beads per construct, and this will make you enough beads to assemble about 36,000 genes. At the 1536 level, economy of scale start to kick in even more, and so with an investment of about $16,000, with a cost of about 3 cents of beads per gene, you'll be able to assemble about just over 500,000 genes. And so in terms of the actual assembly itself, here I'm showing the cost and the proportion as relative to total at the 384 level and the 1536 level. And what you can see is that especially once you start getting to larger and larger scales is that the cost is really dominated by the cost of the underlying oligos itself. So what, and I should say that the total inclusive cost that we estimate is somewhere in the above $1 region and maybe 75 cents at the 1536 level. And so what this really says is that you should really negotiate very strongly with your array providers to get the best possible price if you really want to get a good deal on or get a good cost of what you're actually gonna have for your DropSynth library costs. All right, so I'm now gonna walk through a typical timeline of what it is that you're actually gonna be doing if you decide to actually go through this. And so when we've done these workshops in the past, we've been able to train people in basically the span of a week and going through pretty much every single step of the protocol. If you don't have beads made beforehand, then that is something that you have to do before you start the assembly. And so making the beads typically involves, it starts with hybridization of 3 different oligos. So there's 2 different oligos here we call the ligation and the anchor oligo, which we order with modified biotinylated ends. And we separately ordered a 384 or 1536 barcoded oligos, which have a common conserved region and the particular barcode sequence, which I'll tell you where the files for those sequences we use. And the barcode sequences I didn't mention yesterday have been specifically designed to maximize the Levenshtein distance in between them to prevent cross-hybridization. And so the typical protocol involves hybridizing all of these oligos together. And so I should mention that at each of these steps along all of these, you still have to maintain everything separated in parallel. So you can imagine you're going to have to do 1536 different reaction on 94 or 384 well plates. And so that involves hybridizing the oligos together, then ligating the ligation oligo with the microbead oligo with the T4 ligase step in here, and then subsequently phosphorylating the barcode so that you can ligate it once it's captured a fragment. We don't order them phosphorylated in order to save costs. And then binding them to stripped avidin coated magnetic beads. There are likely other formats that you could use to save costs if you're really interested in scaling this up. Washing anything that's unbound away, and then pulling all of the different beads together. And so this washing step can really be tiresome, and I'll talk a little bit about the kind of equipment that you should have to really save you some time there. Or buy some. So if you're interested in actually doing this, contact me, because I'm trying to get something together where I can probably through the core at University of Oregon sell some of these beads, since they're primarily the largest activating barrier towards people actually using this technique at the moment. Or if you know companies that are interested in actually making those barcoded beads, I'd love to hear about them. And so we had this recent paper from authors at UW who mentioned that DropSynth required specialized equipment. This is true. So unless you, several years ago when I first made the 384 bead pool, I actually did it manually using a multi-channel pipette. I would not recommend anybody ever try that. So see if you can find a local Rainin liquidator or a ViaFlow for your bead preparation, which will really save you a lot of time, particularly in all the mixing and aliquoting and washing steps. And so with these, it becomes relatively simple to make the both 384 and 1536 pools. All right, so I thought this would be covered earlier, but I don't think it has. One of the kind of lures in subpool assembly is when you order your chip with many defined subpools with orthogonal primers on there, you have to amplify it off of the chip in the first step. And so in order to prevent over amplification, which leads to all sorts of unwanted products, you basically have to do an initial qPCR and basically stop or determine at what cycle you're basically ending your exponential phase before you reach the plateau. And so once you know your cycle number, you can go in and do an amplification off the oligo chip. Here I'm kind of showing you if you run a gel off of a pool that you've amplified, this is what you'll see if you do your amplification well versus if you starting to get over amplification. You basically see the formation of these higher molecular weight products start to show up. And so that's a good sanity check. Of course, you can always do a size selection as well. Okay, so I'm skipping kind of one step here, but it's relatively straightforward. Once you have isolated each of your subpools, you then go and do a bulk amplification in order to have several micrograms of DNA. And then you expose them overnight to a nicking enzyme, essentially nicking on either strand, on either side of that barcode. And then processing the nicked oligos is a little bit of a tricky step if you've not done it before. So to remind you again, what we're doing here is we're essentially removing this small fragment. This small fragment is biotinylated, so we're binding it to a streptavidin-coated magnetic bead, which we're then removing. And so the tricky thing about this step is that, of course, we want this barcode to be melted while you're removing this. And so what you have to do is, here we see a little kind of jury-rigged MacGyvered setup that I was using a while ago, where we've got the tube actually sitting in a water bath while it's being exposed to the magnetic field. So there's a number of different, more elegant ways to do this, but this works pretty well, actually. So all you have to do is just carefully pipette out your supernatant here while keeping the beads on the magnet to recover your processed oligo pools. And then we bind the processed oligos to the beads which you created in the first step, and then we go to an emulsion PCA. And so the first time you try this, I would recommend that you look at your droplets under a microscope. We use a very simple vortex technique where you essentially just mix the aqueous and oils phase, and you put it into a vortexer and let it run at max speed for 3 or so minutes. And so I want to mention several things here. One is that the beads in the Vortex method are highly polydispersed. It doesn't matter, don't worry about it. The bigger problem is if you, as we tried to initially do, try to use microfluidics to get a very monodispersed level of beads, that the BTS alpha 1 type 2 supposedly temperature sensitive restriction enzyme that we use to cleave the payloads off the surface of the bead is actually still really active even at room temperature. Here is what you're seeing here is digestion of a PUC19 vector. And so you see there's still very high activity even at room temperature, and it turns out even on ice. And so unless you have a microfluidic chip that's able to really flow a lot of volume very quickly, if you have your actual reaction with the restriction enzyme in there sitting for a while, even if it's sitting on ice within your syringe or whatever you're using, then that could lead to premature cleavage of the payload sequence from the surface of the bead before it's in a droplet, which could lead to all sorts of cross-contamination and chimeral products and essentially failure. But the Vortex method works really well, and it's extremely simple and doesn't require any kind of specialized equipment. There's a number of different ways to then recover the subsequent assembled libraries. And so this requires doing an extraction using either chloroform or PFO. How many people in the room are familiar with phase lock gels? Okay, so some people know what a phase lock gel is. So a phase lock gel can be something that's extremely useful when you have to pipette the aqueous portion away from the organic portion in such a way that you don't end up getting any of the chloroform in your resulting downstream steps. And the way this works is, and very easily, there's biotech companies that will sell you these at extremely ridiculous cost, but you can buy some Dow Corning high vacuum grease and slap a bunch into a tube, centrifuge it, and then you'll get a really nice kind of gel layer in between your organic phase and your aqueous phase, and you can just easily kind of pour out or pipette the aqueous phase out. And so finally, what I want to mention is once you break your emulsion, you need to do a size selection step. after you recover your initial assembled library, you may or may not see anything on the gel. So you may see a product there, or you may have to do a completely blind extraction, which is a bit intimidating the first time you do it. But we've integrated in the latest version of the protocol a suppression PCR step. And so the suppression PCR step essentially involves adding inverted terminal repeats to the ends of your product and suppresses the formation of low molecular weight products, essentially driving their reaction towards the higher molecular weight assembled products that you're actually interested in using. Yeah. And so in terms of computational design, everything you need to know is kind of on the website we built, dropsynth.org. There's a link to the scripts. My apologies, it's still a little bit messy. We just don't have the resources to clean them up at the moment, but they will be at some point. And in the sequences section, you will see all of the 15 mer primers necessary for subpool amplification, the assembly primers that are necessary in the actual DropSynth reaction, although these days we're basically only using one single one. All of the sequences necessary for the microbead barcodes at the 1536 and 384 levels, as well as the sequences of the ligation oligo, anchor oligo, and the corresponding oligos that you need to synthesize for the beads. And so the only other thing I want to mention with these scripts is that they'll take input as amino acid sequences in the form of FASTA files. They do require a small little modification in the case where you're not working with protein sequences and you need to assemble just nucleotide sequences. Very quickly, the way the script works is that it takes an amino acid sequence, assign random weight codons based on some codon frequency table from your particular organism that you're targeting. It'll add, well, whatever sites you want for cloning or whatever method you use for cloning. I can talk a little bit about that. Using restriction enzymes, obviously a little bit primitive, but it does give you freedom to basically do fusions or choose any kind of ribosome or C-terminal fusion that you're interested in doing. There is a step built into the script here, which actually adds a random buffer in such a way that it'll actually make your size selection step easier. And so you can imagine if you're synthesizing a library with a relatively large length distribution, it can be a little bit problematic to then actually, take out a big piece of your gel and just essentially size select on that. So we've added a buffer in that can help narrow that all into a single band. We then add assembly primers, split the oligos into sequences, see if this fails or not, and then possibly do this several times. And then for each oligo, we add the restriction enzyme necessary to remove it from the beads, another buffering region to make sure that all our oligos are the same length. We add the microbead barcode and amplification primer, and then you're done. And so that's all I had to say. Happy to take your questions.